All right, everyone. Today we've got a really nice irregular pentagon problem. And I want you to see exactly how a professional solver would think through this, step by step. So let's dive right in, and please remember to like, subscribe, and drop a comment. If you find this helpful, it really does help the channel grow. So here's our shape. We have this irregular pentagon called PQRST, and right away notice something important. There are 3 right angles marked in this figure at vertex Q, at vertex S, and at vertex T. And that little detail is going to be the key to everything we do today. Now let's look at what we're given. We know PT equals 15. We know TS equals 16. We know SR equals 48. And we know RQ equals 60. And our job, the thing we're hunting for, is this unknown side PQ, which we're calling X. Now here's the challenge. This pentagon is irregular, so we can't just slap the Pythagorean theorem on it directly, because it's not a triangle. It's a 5-sided figure, so we need a clever trick to break it down into shapes we actually know how to handle. And that trick is building an auxiliary rectangle. Let's look at this step carefully. We're going to introduce a brand new point. Let's call it U. And we're going to draw it in a very specific way. We want segment US to be equal in length to segment PT, and we want US to run parallel to PT. And then similarly, we draw segment UP so that it equals segment TS in length, and UP runs parallel to TS as well. Now notice what happens here. By constructing U this way, we've actually created a rectangle, specifically rectangle UPTS, going around from U to P to T to S. And why does this matter so much? Because a rectangle has some beautiful guaranteed properties. Opposite sides are always equal. Opposite sides are always parallel. And all 4 interior angles are exactly 90 degrees. No exceptions. So, let's use those properties immediately, since US equals PT, and we already know PT is 15. That tells us US equals 15 as well. And since UP equals TS, and TS is 16, that means UP equals 16 too. And because it's a rectangle, the angle sitting at vertex U has to be 90 degrees. That's just a guaranteed fact about rectangles. So keep that in your back pocket for later. Now here's a really elegant part of this construction. Once we've built this rectangle, points U, S, and R all end up lying on the exact same straight line. They're collinear. And the reason that matters is that it lets us just add lengths together like we're stacking blocks. So the full length from U to R becomes US plus SR. That's 15 plus 48. And if you add those together, you get 63. So UR equals 63 units. Hold on to that number. It's going to be really important very soon. At this stage, we don't need segments PT and TS drawn into our working diagram anymore. They've done their job. They helped us build the rectangle and figure out UP and UR, so mentally. Or on your whiteboard, you can simplify the picture down to just the essential triangles now. Now here's our next big move. We're going to connect point P directly to point R with a straight segment and pay attention to this simplification. Because this single line does something really powerful. It splits our whole figure into exactly 2 right triangles. Triangle UPR on one side and triangle PQR on the other side. And here's the beautiful part. Both of these triangles share the exact same hypotenuse, which is segment PR. That shared side is going to be our bridge connecting the two triangles together. Let's look at this step carefully now. We're going to focus first on triangle UPR. And we already established that the angle at U is 90 degrees. So this is a right triangle, which means the Pythagorean theorem applies perfectly here. Quick reminder of what that theorem actually says. For any right triangle, if you take the two shorter sides, called the legs, square each of them, and add those squares together, that total equals the square of the longest side, the hypotenuse. That's the relationship leg squared, plus leg squared equals hypotenuse squared. So, in triangle UPR, our two legs are UP, which is 16, and UR, which is 63. And our unknown hypotenuse is PR. So we write 16 squared plus 63 squared equals PR squared. Now, let's actually compute these. 16 squared is 16 multiplied by 16, which gives us 256. And 63 squared is 63 multiplied by 63, which gives us 3,969. From the previous equation, we get 256 plus 3,969 equals PR squared, and adding those together gives us 4,225 equals PR squared. Now, to undo that squaring and solve for PR itself, we take the square root of both sides, and the square root of 4,225 works out very cleanly to 65. So PR equals 65 units. And remember, this is huge, because PR isn't just the hypotenuse of this one triangle. It's also the shared hypotenuse of our second triangle, triangle PQR, so we already know one of its sides without any extra work. Now, let's shift our attention to triangle PQR, and notice this triangle has its right angle sitting at vertex Q. So once again, we've got a right triangle, and once again, the Pythagorean theorem is exactly the tool we need. The two legs here are RQ, which we know is 60, and PQ, which is our unknown x, and the hypotenuse, as we just found, is PR, which equals 65. So we set up our equation, x squared plus 60 squared equals 65 squared. Let's compute those squares one at a time. 60 squared is 3,600, and 65 squared is 4,225. So our equation becomes x squared plus 3,600 equals 4,225. Now, the reason we can do this next move is that we want to isolate x squared all by itself. So we subtract 3,600 from both sides of the equation, and that gives us x squared equals 4,225 minus 3,600. And when you carry out that subtraction, you get x squared equals 625. And finally, just like before, To solve for x itself, we take the square root of both sides, undoing that square completely. And the square root of 625 comes out to a nice clean whole number, 25. So x equals 25 units, and that, right there, is our final answer. The unknown side of this irregular pentagon is 25.